Hey guys, this video is about acids and bases. It's basic introduction with definitions and then how to find pH, pOH, hydrogen ion concentration, and hydroxide ion concentration. Alright, so this is a basic pH scale, and what we see is the pH down here from 0 to 7 is acidic, at 7 it is neutral, and then above 7 is a base. It's also called an alkaline. Okay, so if you see alkaline, that means bases too. So as you can see, the pH down here, let me get my thing. The pH down here from 0 to 1 is much lower, which means it's a better acid than a pH that has a higher, a pH of 3. And then bases have a much higher pH. Strong bases will have a pH around 13 to 14, as long as it's concentrated, and then weaker bases are down here, 10, 11, 12. All right. So properties of acids that you need to know. They're going to have a low pH. They usually taste sour, so you can think of citric acid, lemon juice, orange juice, that kind of thing, citric acid, vinegar, which is acetic acid, is going to have a low pH, and the hydrogen ion concentration is going to be greater than the hydroxide ion concentration, because acids have hydrogen in them, right? And then alkaline or bases, they're going to have a high pH, and they're very slippery. If you've ever gotten bleach on your hands, bleach is a base, and if you've ever gotten on your hands before you wash them off and your hands get all dry, if you rub your fingers together, it's really slippery. It feels like you have oil or something on your hands. All right. So before we can talk about pH and all that stuff, we need to talk about the 3 types of acids and bases. The first type is the areneous acid and base. So the definition of an areneous acid is that it's a substance that donates a hydrogen ion in solution. So it gets rid of a hydrogen ion in solution. And then a base donates a hydroxide ion. So if we look at this as an example for the acid, if we put HCl in water, then it's going to produce, what happened? It's going to produce hydrogen and chloride. It's going to completely dissolve in water. And then a base, like sodium hydroxide, dissociates completely to make hydroxide. So those are examples of an areneous acid and an areneous base. Now the reason that these dissociate this way is because they're both strong, and so they completely dissociate. So any amount of hydrochloric acid that you have is going to make the same amount of hydrogen and chloride, and any amount of sodium hydroxide that you have is going to make the same amount of sodium and hydroxide. All right, so a Bronsted-Lowry acid. So as time went along, Bronsted-Lowry redefined it, because not everything that they encountered that had a high pH or a low pH was considered an acid and base because of the definitions that Arrhenius had given them. So the acids still donate hydrogen ions, but the bases accept them. So if we look at this example, okay, that's a negative charge up there. If we look at this example, ammonia here, going from here to here, has accepted a hydrogen ion, and so that's a base. And water, on the other hand, has lost a hydrogen, and so that's an acid by Bronsted-Lowry definitions. And then we have one more that I want to talk about briefly, very quickly, and that is the Lewis acids and base. All I want you to know are the definitions of these. So, all right, so Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. And so even though it looks like they have switched roles, they haven't. A Lewis acid and base could never turn a Bronsted-Lowry acid into a base. This just broadens the definition of what an acid and base are. So we could take salts and things that don't necessarily accept a hydrogen ion, but accept other things that are positively charged, and they act as a base. You don't have to focus on that. I just want you to know the definitions right now. So don't focus too hard on that. Just know that Lewis is the opposite in accept and donate, but it's also the opposite as this is doing negative charges, while these are positive. All right, so we'll go back over Bronsted-Lowry in more detail because that's what we're going to focus on more than anything. But right now I want y'all to just be able to do the calculations that we're about to start. Before we do that, we need to go over strong acids and strong bases. Now, strong acids dissociate 100%. So these are the strong acids you need to know: hydrochloric, hydrobromic, hydroiodic acids, nitric acid, chloric acid, perchloric acid, and sulfuric acid. So these acids dissociate 100%, and what that means is that if I have hydrochloric, it completely dissociates into hydrogen ions and chloride ions. If I have something like hypochlorous acid, HClO, which is not on this list, it does not dissociate all the way, and it goes into equilibrium, and so it changes everything. All right. For the first couple of days, we're only going to talk about the strong acids, but you need to know them so that you can tell the difference between them. So the only way to know them is to memorize them. Sorry, but that's the way it is. Strong bases are the same way. These are the 8 strong bases, and to memorize them is very easy. As you can tell, all of these are the metals from group 1A off the periodic table, and these are the last 3 metals from group 2A off the periodic table. And so if you look at the periodic table and you have a little bit of imagination. Why is my pen not working? Okay, it looks like a B. All right, so as long as you know the charges from the periodic table and you know that these guys are right next to each other, they make strong bases. So any other base that you find would be weak. All right, one more thing, water is amphoteric, and what that means that it can act as a base or an acid. Okay, so I know that sounds kind of crazy, but if we look at this reaction where water is reacting with water, and so this is happening in a glass of water, then one hydrogen could go to one water, so it's accepting the hydrogen, so that's going to be a base, and then one is losing one, so the other one would be an acid. There's a relationship that comes from this reaction. I'm not going to get into how it's found, but I am going to write it down. and its Kw is equal to the concentration of hydrogen times the concentration of hydroxide, and the Kw at room temperature is equal to 1 times 10 to the negative 14. So that gives us this equation. And we'll be able to use that later on. Okay, so know that water is amphoteric, and know that Kw, 1 times 10 to the negative 14, is equal to H, the concentration of H, times the concentration of OH. All right, so now we can get into pH calculations. So pH is a numeric scale used to specify the acidity or basicity, and it's related to the hydrogen ion concentration. And so the equation to find the pH is pH is equal to the negative log of the concentration of H. So I know this is scary, especially for some sophomores, but guys, log is just a button on the calculator. You'll learn more about logs in algebra, maybe some pre-cal, but don't freak out about it, because in chemistry all I care about is you being able to press the button on your calculator. And so if we look at this example, I have 0.5 molar hydrochloric acid, and I want to find the pH. And so in order to find the pH, I need the hydrogen ion concentration, right? Because pH is equal to the negative log of the hydrogen ion concentration. So we know that HCl completely dissociates into hydrogen ions and chloride ions. So if I have 0.5 of this, and it all turns into hydrogen and chloride, then that means I'm going to have 0.5 molar of that, and chloride too. So since this is the concentration of H, that's what I have to plug in here. So in my calculator, I'm just going to press negative log of 0.5 and then hit enter. And what I end up getting is 0.30. So that's my pH of a 0.5 molar hydrochloric acid solution. All right, so next we're going to find the OH. And if you remember, the equation that I had on the slide before was 1 times 10 to the negative 14 is equal to the concentration of hydrogen times the concentration of hydroxide. And so since we have the concentration of hydrogen, I can plug that in here, and I can solve for OH. So I'm going to do that. So divide both sides by 0.5. So the hydroxide concentration is going to be 1 times 10 to the negative 14 divided by 0.5. And if you put that into your calculator, what you find is that the hydroxide concentration is equal to 2 times 10 to the negative 14 molar. So that's my OH. All right. Now the POH is another scale. It's just the opposite of the pH. And so the POH is just the negative log of the OH. So remember what we had. We had pH is equal to the negative log of the hydrogen concentration, the H. And so the POH is equal to negative log of the OH. So P, really, all P means down here is to take the negative log of whatever is sitting behind it. And so in the last problem that we had 0.5 molar H plus, and we had a pH of 0.3 and an OH of 2 times 10 to the negative 14. And so we want to find what the POH is. So I'm going to plug in the hydrogen ion concentration of 2 times 10 to the negative 14 into the log equation. And so the negative log of 2 times 10 to the negative 14 is found to be 13.70. Now this is interesting because if you remember the pH scale that we looked at on the very first slide went from 0 to 14. And if we add the pH plus the POH together, so the pH was 0.3, right here, and the POH we just found to be 13.7, it gives you 14. And so the pH plus the POH will always be 14. You may get a pH less than 0. You may get a pH greater than 14. And same for pOH. But as long as they add together to give 14, then you haven't made any mistakes. All right? Okay. All right, so finding H and OH from pH and pOH. So from earlier problem, these are the calculations that we had a 0.5 molar hydrogen ion. We had a pH equal to 0.3. We had a hydroxide concentration of 2 times 10 to the negative 14. And we had a pOH of 13.7. So before we do this, I'm going to write down these equations for pH. So pH is equal to negative log the concentration of hydrogen. And so if we wanted to solve for hydrogen, the first thing we would do is we would get rid of that negative sign. So if I get rid of the negative sign, I get negative pH is equal to the log the concentration of hydrogen. So how do we get rid of log? What is the opposite of log? When you look at a calculator, a TI calculator, the second, if you press second and then log, you get 10 to the x. Okay, so there's lots of different bases you can use with logarithms, but we use base 10 for acids and bases. So this is the opposite of log base 10, to take the relationship and put it to a base of 10. So if I wanted to undo this right here, I'm going to take 10 down here on the bottom like that, and that gets rid of this. So I want to take my pH that I have right here and calculate my hydrogen ion concentration. Now we already know what it is, it's 0.5. We'd started with that, but I want to prove to you that this is the right equation. So in your calculator, what you should do is you should plug in, press second log, which should give you this, 10, right? And then press negative 0.3 and hit enter. And that should give you 0.5. So that's the hydrogen ion concentration. Because all you have to do is take 10 to the negative pH, and that gets you the hydrogen ion concentration. So if this is the relationship for H, then this is the relationship for OH, because it's just the opposite of the pH equals negative log equation. All right, so we're going to do some more examples. I wrote the equations up here at the very top so that we could see them all the time. I suggest you get a sheet of paper, you write them really big and really clear and spread them out so that you can see them all at the same time. It makes it a little bit easier. Okay, so for the first example, we have a 0.23 molar strontium hydroxide, and we want to find pOH. And so the first thing I have to do in order to find pOH is I have to know what my OH is. And if we have strontium hydroxide, this dissociates completely. And so if this is 0.23, strontium will also be 0.23, but hydroxide will be 0.46 because it's twice as much, because there's 2 OHs for every single one of these. So our OH is going to be 0.46. Oops, that doesn't look like a 4. I don't know what that looks like. So to find the pOH, let me bring my equations down here. To find the pOH, we're going to take the negative log of the OH. So if I take negative log of 0.46 in a calculator, I end up with 0.34. And so this is my POH. All right? Okay, so here's some more examples. This comes from a table from one of the worksheets that you've gotten. We're looking for the concentration of sodium hydroxide, concentration of hydrogen. We're given the concentration of hydroxide, and we're looking for the pH and the POH. So if this is the only piece of information that I have, I'm going to find the easiest thing first. So I'm going to find POH first, because that's simply just the negative log of the OH, and I have this. So if I put negative log of 0.1, I'm going to try to write this down here small. I might have to shrink my pen, so I'm sorry if you can't see it on the screen. Negative log of 0.1, right? Then what I'm going to end up getting in my calculator is 1, right? And then I can next find the pH very easily, because the pH and the POH have to add together to give 14, right? It's right here. So these two are going to add together to get 14. So if the POH is 1, that means that the pH is going to be 13. So next I have to find the hydrogen ion concentration. And so to find the hydrogen ion concentration, I'm going to use this right here. The hydrogen ion concentration will be equal to 10 to the negative pH. So in my calculator, I put second log negative 1,3. And so you would get out from that 1 times 10 to the negative 13. So again, I'm going to write it really small. That's 10 to the negative 13 in your calculator. And you can see that it's going to be this. Multiplying by 1 doesn't change anything, so it's the same number. All right, so, and then we're going to find the concentration of sodium hydroxide. And so sodium hydroxide gives you hydroxide. It doesn't give you hydrogen, it gives you hydroxide. And if the sodium hydroxide gives you 1 hydroxide, then that means the concentration of hydroxide has to be equal to the concentration of sodium hydroxide. So this is going to be 0.1. All right, so let's do the next one. Here we have nitric acid, and we're given the concentration of hydrogen starting out. So the first thing I'm going to do is find the pH. And if we take the negative log of 2, because that's the pH equation, right? It's right up here. Then you get in your calculator negative 0.30. And so then I'll find the POH next, because these two right here have to add together to give 14. So this is going to be 14.30, because this one's negative, so this one's going to be above 14. All right, and then the hydroxide is going to be 10 to the negative POH, which is 14.30. And so I think that that is 5 times 10 to the negative 15. Yes. Okay, you can't read that at all. Hold on. All right, that's a little bit better. And so now for the concentration of nitric acid gives hydrogen because of that. So my concentration of nitric acid will be the same as my concentration of hydrogen, because there's only 1 hydrogen and it's a strong acid. So that's 2 molar. All right, we're going to do one more. Whoopsie. And I'm going to bring the equations down here. Let's see. This might take me a second. All right, so we're going to find the pH for a 5-gram hydrochloric acid solution in 2,000 milliliters. All right, and so we want to find the pH. And so to find the pH of this, I need the concentration of hydrogen. So in order to find the concentration of hydrogen, I have to figure out what the concentration of HCl is first. So I've got 5 grams of HCl, and I need to turn that into moles so I can get moles per liter. So there's 36.5 grams in 1 mole. That's the molar mass. And if I take 5 and I divide by 36.5, I get 0.137. So there's 0.137 moles in 5 grams. And then I have to divide that by 2 liters because 2,000 milliliters is equal to 2 liters. And so that gives me a concentration of 0.0685. And so this is my hydrogen ion concentration. So in order to find the pH, I'm going to take the negative log of that number. So if I put that in my calculator, negative log of 0.0685, I get that my pH is equal to 1.16. All right, that's it. I promise if you try a few of these, it will start to get easier and easier, and then eventually you'll go, why was this so hard to begin with?